Hello, Bern. My name is Cristian. He is Anatoly. We are two engineers at a company called Zendesk. It's a pretty big company. Who here uses Zendesk? Few people, nice. So we are going to, well, first of all, I would like to say that this is our first presentation. We've done it in a few places before, but the point is that I'm personally very sorry for what is about to happen. Hopefully you forgive us. And first of all, I want to comment about the topic itself. Why this presentation? Well, this is an important presentation because we talk about one of the biggest questions for humankind. Does Rails scale? And I have something to tell you. There is some of you here that have a secret. Some of you went to computer science school, like in college. Who went? Okay, and some didn't. And the ones that went to school, we have a secret that we don't share. I'm going to take you down a trip to memory lane. You remember your first day when you arrived to school, and that first day they teach you two things. Those are very, very important ideas that have served me very, very well across my whole career. There's a picture of my teacher those times. The first idea is Ruby is dead. Believe me, I've been doing Ruby for 15 years. It was dead 15 years ago. So it's really dead right now. The second one, and is the one that we're going to talk now, is Rails doesn't scale. It is known. Okay. People are talking about this all the time. Like a couple of months ago, programming Twitter was again talking about this, all because of this tweet. I don't know if you remember what happened. DHH, our fearless leader, basically decided to remove TypeScript from, I think, the Basecamp repo. And if that wasn't provocative enough, he decided to publish it in Twitter and cause a flame war. Of course, because DHH is the founder or creator of Rails, people start to attack Ruby, And I found this tweet I found it very funny. Like, all languages have some kind of deep insecurity. And the one in the Ruby community is that Ruby doesn't scale. It's funny because similar languages, like, I don't know, Python is a bit faster, but it's kind of in the same ballpark, I would say. People don't talk that much about this. But for Ruby, it's all the time. Ruby doesn't scale. Don't start your startup in Ruby. It's going to fail. The point is that this is just not true. Like, there is plenty of companies that use Rails. Some of them don't use it anymore, but for example, Shopify uses it. Zendesk will use it. So it's just scales because there are companies working at scale with it. It's just a fact. It's not debatable, really. Moreover, if you want to know more about that, it's actually a good day because today is Black Friday. Last year, Shopify made a thread about all the scalability and performance level that they achieve with a Rails monolith. So I think I proved already that, okay, this doesn't really make sense. There's people using Rails serving 75 million requests per minute. So from where this idea comes from? I have an explanation. But for the explanation, you're going to have to time travel a little bit with me. I don't know if you know this guy. He's called Doraemon, the cat. But don't worry, later we'll talk about Doraemon. First, we'll travel to 2010. That was me. Actually, that was not me in 2010, but I like this picture. And I was writing my first Rails app. It was like a very small magazine, like movie magazine. And this magazine needed authentication. I needed the reviewers of the movies to have their own back office and write reviews. The thing is, authentication is a hard problem. Later, with the years, I became tech lead for the authentication team at Zendesk. And just encryption is like mind-boggling. It's really, really hard problem. But then at 20 years old, I had no idea. So I said, OK, I'm going to do this kind of very deep, thorough investigation. I checked everywhere I could. And of course, I found device. I just read the documentation. I had a couple of lines, ran a migration, if I remember correctly. And that was it. It worked. Authentication is a hard problem. But for 20-year-old me, it felt that this is super easy, and I am the master of the universe. It felt really, really simple. OK, the second part of my explanation requires us to move again in time to 2012. And I just use this because I really like this picture. And in 2012, I had the very important role of Chief Technical Officer in a company called Playful Bet. I achieved this position of chief technical officer inside of the company being the only engineer, which made it even more challenging the fact that we had to scale. We became very popular in between well, young people in Spain, and we were for a while one of the applications with the most traffic in Spain, and I was the only engineer, so that was hard. And scaling is a hard problem. I hope that's probably why you are interested in this presentation. So again, I follow the same strategy. Do a deep and thorough investigation via the best sources I could find. And of course, I found this gem, ActiveScale. Who here uses ActiveScale in production? Well, okay, well, surprising. So I read the documentation, I decided to go for this. Scale, Rails scale, sufficient but not too much. Honestly, later you can change the parameters to use, for example, Go bananas. That's the best one. And that was it. Everything was beautiful and nothing hard. Thank you. I told in the beginning that, that I am sorry for what was going to happen. Okay, that's not true. ActiveScale doesn't exist. Actually, I just changed, I think, active support. Like I just modified the title with Chrome. But my point here is that scaling is a hard problem. But it's a problem that feels hard. You don't get a free lunch like with device that I have absolutely no idea what encryption is, but I have in my system a really consistent solution. There's no way to do that. So the conclusion is not that Rails doesn't scale. It's that Rails is so good that one of the few problems left for you to solve is scaling. Okay, but how do we make Zendesk scale? Well, before going to this, I want to give some general concerns, some general ideas about the presentation. We are going to be very general. We're not going to get very deep into anything. We don't have the time. We will give you general ideas and we will illustrate them with, well, issues that we found while scaling Zendesk. This is because we found that there are no silver bullets. If someone comes to me after this happens sometimes, oh, how can I make your system scale? It's like, I have no idea, I don't know your system. Typically can be database, but there's so many reasons why a system doesn't scale. Tolstoy said something like this, no? Every poorly performing system is performing poorly in its own way. Moreover, the size of the problem. And you will be asking why this guy thinks he's qualified, me and Anatoly actually, to solve this, to comment about this. It's because at Zendesk we manage certain performance problems. So Zendesk is a customer support product. So basically if you complain about anything, I don't know, this mattress I bought is broken or whatever, you send an email to the company and this generates what is called a ticket in the customer support industry. At Zendesk currently, actually these are all data, we have over 20 billion tickets. Just to give you an idea, I could give 2.5 tickets for each person on the earth, including babies, and there was still a few left. Moreover, the data set grows. Around a third of the tickets are created during the last year. This has an obvious effects in our system. Only in relational databases, and we have other kinds of stores, we have over 400 terabytes. Probably this point is more like half petabyte. And one thing I want to discuss is that this is not all our data. We have a lot of different data not in the relational database. Just to give you an idea, we have a model of which we have trillions of those objects. It's something we use for auditing. We have trillions. Good luck running a query on a trillion objects. But okay, these were the general ideas I wanted to give, and now we finally get into the topic. The first thing that you need to know about performance is monitoring. And the reason is that you cannot solve a problem you don't know you have. Sometimes you may be surprised. All of us think, oh yeah, this endpoint is slow. Well, actually no, maybe you have another endpoint that is way, way worse. So just monitoring is very important. However, you will find that when you have a very big system, a very big application, monitoring can become super expensive. And literally, it's like sometimes we found that if we misconfigure our Datadog instance, it's like we will burn all the money of the company easily. One thing that works very well for monitoring performance is sampling. The reason is that, for example, when you're logging, you need everything because there could be an error. It's important to have the whole data. For performance, what you want is the patterns. So a 10%, even sometimes a 1% of the data can work good enough for you to make a diagnosis of what's happening in the system. Once you have all that data, the next step is doing an error budget. And then you may be thinking, if you're familiar with the concept of error budget, is that how is this related with performance? An error budget is like uptime. This is up for the 4 nines, 99.99% of the time. Well, you can define an error budget for latency. You can say, okay, whatever, our systems has 5 nines of uptime, but if my endpoint is returning a 200 after 1 minute, maybe it's not really working. We really do this at Zendesk, not with 1 minute, but with more reasonable times. If you check in the left column we have, this is 3 different endpoints, by the way, of our application. In the left column is the traditional uptime, the amount of time our application is up. In the center is what we defined as acceptable amount of time. I don't know how much it is, but maybe we're talking about 500 milliseconds for a show or 300 milliseconds, I don't remember. And in the right, we have the good amount of time. I know that it sounds like, well, how do I decide what's a good amount of time and acceptable amount of time? Yeah, we can have a debate about that, but this is not really the most important part. The important part is to have a North Star. So you can detect if something goes wrong, that something went wrong. And next, Anatoly will explain us how to maintain those error budgets happy.
The phone, no.
Yes.
Hi, everybody. Anybody asleep? Now awake? Okay, that's good. I have interesting slides about database performance. I started to work with Ruby in 2008. Anybody remembers Ruby 1.8.7? On Rails 2.0.2. Okay, this talk is for you. No, I'm kidding, for everybody. Let's talk about database performance at Zendesk. What are the type of problems we try to solve at Zendesk? So why do we ever talk about a database in this talk? We have a cost optimization aspect, and this is what we have to keep in mind when we watch the next 20 slides. Next slide. So what Zendesk databases are today? So we have a rapid data set growth. If you know that we created 30+% tickets in the past 2 years, that's a lot. So we run in AWS. We run AWS Aurora databases, MySQL and Postgres. And we recently right-sized databases. Yes, so we saved cost while we kept performance. And let me tell you how. Anybody thinks that the application performance problems is the database performance problems? No. Okay, let me prove it that it's the case if you have like application like Zendesk size. Imagine you have a full table scan. Select a count from table with 100 rows. And then you have a problem with select from 100 million rows. Anybody thinks that the response time will be the same? So this is the hint which will help to understand the next slide. 3 myths working with a large databases like Zendesk have today. Spiky workload can scale. We learned the hard way that the spiky workload cannot scale. If you have spikes, the spikes will only go higher and higher and higher. More hardware you put to the problem. Second myth is downscaling can actually degrade performance but not improve it. Well, this is a myth, you'll see why. And volume of data doesn't change query performance, or it of course does. If I give you 2 pills to choose from, so imagine that you have application like Zendesk with billions of rows, billions of records in the database, millions of customers, and you have a performance problem with the application. What do you think may happen with the database if you downscale it? Will performance get better or worse? Okay, watch next. We developed this 3 steps approach, which actually helped to prove to be very efficient thing. Right-sizing database, which often means downscaling, detecting the problems and then reaction. First of all, a large infrastructure, large amount of CPU cores in the memory prevents you from seeing the root cause of the many performance problems. You think it's application problem, but it's the database problem instead. So if you have a spiky workload like you see in the next slide, you'll understand what I'm talking about. Anybody familiar with this type of situation when the database works fine and successful and performant, and then boom, you don't have anything like any resources left available? What happens if you upscale, if you throw twice more hardware or 4 times more hardware? Well, what if your cloud provider doesn't have anything larger than that? What if this line is the maximum it can give you? You come to AWS and you say, I need more. And you hear the silence. This is the type of spiky workload I will show more. And this is the type of spiky workload that can prevent you from right-sizing your infrastructure and hide the problems. But to see this problem, you have to narrow down and zoom in to very little, like 9 minutes, maybe less than that. Because you don't see this problem along the day. It doesn't happen. But when it happens, you don't know why. What are you going to do? Next slide will show you some real example which happened 2 months ago. We run a very interesting experiment at Zendesk. We knew that the second largest application at Zendesk has performance issues. And the reason why was the memory drops, which happened once a week, twice a week. And we didn't know, we had some theories why did it happen, but we didn't know exactly why did it happen. What you see on the graph is the freeable memory. It's the amount of memory available for your database instance. First line, maybe 10 centimeters. What you see is a flat line. That means no load on the database, no traffic, no queries, nothing. Flat line is expected. And then you start to see some drops. We started to move some customers and see some performance issues, but that didn't happen too often. They happen once a week. And I want to tell you that each drop means the database crash. When a database crashes, you expect some application failures. Anybody still thinks that the database problem is not application problem? Or vice versa? So if application has if you have SLI and SLO, and you don't have, and it's red, it's not green. But the problem is not the application logic, business logic, or algorithm, is the data structure. Each drop you see on the screen is a database crash. And what happened on this project? In the middle of the screen, you see the line halved. So that was the downscale first time. But we didn't stop there. We downscaled again at the end. Before that, we saturated databases to the point when problems start to happen every day, like not every week. And we used downscaling as the microscope to see, okay, what exactly happening, why did this happen, and what to do about it. And at this point, it became super clear. Okay, this is the problem. Every engineer understands, okay, this is not application, this is database. What we're going to do with database? Solution was the application change, yes, but we need this microscope to detect the problem first, and then downscaling from 16XL to 4XL became obvious solution. And if you know the price of AWS Aurora, you understand how much difference is it. Well, of course, downscaling is not solution to every problem. You have computation-intensive workload when utilization is flat and you don't have any spikes. Yes, upscale as you want, you'll get flat, you'll get expected performance along the way. IO-intensive applications, think twice. Think about throwing more hardware before you saturate the database and see more. And I actually have some theoretical material behind this exercise, so it's not just random game day. let me show Amdahl law and Pareto principle. Anybody has stateless application without database in the room? Yes. So what you have is the stateless chart. So this linear graph means that you can offer more. You can throw more. Sorry. You can throw more requests, more traffic at application, and you expect consistent performance and completion of your queries. In the real system, well, in the real system, sorry, I have to say, in a system with the database, relational database first, you will get the point of contention where you start to get some anomalies and performance issues. Even if you add more hardware, you have more queries, eventually you will start to see the decline and then you'll see failure. This is exactly what was happening 5 slides ago. I have 3 last slides. So anybody hear about Pareto principle, 80-20? Any finance people in the room? Okay. So think about database as a think about database as kind of a very closed system with some problem, but you don't have to solve them all. You have to solve only part of the problems to get cost reduction if you care about the cost. But if you don't care about the cost, you maybe care about performance. So, and 20% of your queries consume 80% of the database resources. If the database is overloaded and spikes happen all the time, it's not all queries, it's only 20%. And 20% of the queries, it's almost everything all your application may need. You don't need them all. Some of the queries you may be able to cut down and don't run anymore. So you can get performance gains, cost improvements. Yeah, that's my part.
Okay, so I'm back. And one thing is that the most important part of this presentation, most probably, and the thing that you do the most when you are improving performance is what Anatoly explained. Is the database work. However, there are other techniques that can have crazy impact on that. The first one is caching. I think we're all familiar with caching. The idea is you have a smaller memory storage, or it could be even a key value store. There are multiple ways to do that. That goes faster, and you use it to save certain data that you will use more often, typically. However, there are other variations of this idea that have been very useful to scale at Zendesk. The first one is called write-through caching. The idea would be that instead of refreshing the cache on the read, you refresh the cache on the write. And this, if you know caching, sounds like incredibly stupid because as face value, you are just duplicating all the data in the cache, and then the cache stops being fast. However, this is not supposed to be done for all writes. It's supposed to be done for certain denormalized objects. Imagine you have an account object, and this account has a calculation of customers that have been active in the last month. This query can be super expensive. However, what if every time that the customer gets active, we calculate this and already write it in a cache? The idea here is the normalizing. Here you have an example. You write data to the relational database, which is typically kind of normalized, but at the same time, you write the normalized stuff into a caching layer, into typically a key value store we use at Zendesk, like, I don't know, like Redis is a good example. Like this, when you need to get this derivated, the normalized data, you can get 0.1 speed. It's like automatical. This is a real example of the optimization we did. In the ticket endpoint, that is the most important endpoint at Zendesk, we had a side load called SLAs. Basically, this told how much time an agent had to solve this ticket. And it was kind of expensive. It was adding around 40 milliseconds per query, which is quite a lot. And yeah, you may be thinking, this is not a lot, but give me a second. Just using caching, we were able to reduce it from 40 to 5. And again, 40 milliseconds may not sound like a lot, but at the scale, it is. The other day, I was listening to a story about Meta keeps some engineers there without doing much, except from time to time they solve a bug, And just by slightly optimizing some code, they save $2 million to the company. This can kind of happen. For example, just in this example, this endpoint was getting hit 50,000 times per day. Per 40 milliseconds per 365 days a year, that's 8 days less of computing. And AWS is not cheap. Of course, this has trade-offs. Adding caching and adding even write-through caching adds complexity. You have, for example, duplicated data. You need to do double writes. Caching, the point is that it's not trivial. And yeah, finally with this, we get back to the point that you were all waiting. We go back to Doraemon. We're going to talk now about what I call the Doraemon paradox. But first, let's unveil this mystery. Who is Doraemon? Who knows who is Doraemon here? Okay, very few people. This actually is fascinating because I've been doing this talk in different places. In Poland, almost nobody knew who was Doraemon. I did it in Bangkok, and it was crazy. Like, literally, they tweeted about me talking about Doraemon in a tech conference. But let me explain who it is. This is a Japanese cartoon, and he's a 22nd century cat that has basically a lot of machines in his 4D pocket. These machines work basically like magical items. You can fly with them, you can transport, you can do whatever, actually. And for me, one thing that fascinated when I was small is the 4D pocket itself, because he can fit whatever. Here you see him taking out a door. Sometimes he takes out the boat. It's like you can put any trash, anything fits there. It's a bit like Redis, no? Yeah. But the point here is that Doraemon really works as a fable about software engineering, because each and every episode of Doraemon has exactly the same structure. Doraemon lives in the 20th century in Japan with his friend Nobita, who is a kid, and Nobita is kind of a disaster. He's clumsy. He's the worst, actually. And all the bad things that can happen to him. Like the girl he loves doesn't love him back. He fails at maths. All kind of problems for a kid. And then he's asked Doraemon, "Hey, Doraemon, can you give me a machine that will fix my problems?" And Doraemon hesitates, but gives him the machine. And it works for a while. Because Nobita is not very smart and eventually starts using the machine in ways that he shouldn't. And this ends up in a way bigger disaster that he originally had. I say this because I feel that this happens a lot in technology. Like particularly in technologies that are so high level as Ruby and or Rails. No, we start misusing them in ways that we don't really understand until they break. And then the problem is the technology itself, not us, of course. For example, I think we are, as a community, we do this a lot. I think we are the only community that embraced metaprogramming to a point that was craziness. Like, I literally, when I started doing Ruby, I was hacking method missing all the time, which is completely insane idea. The point is that we should use technology wisely. We should try to understand what we are doing. I don't tell you to read the code base of all the gems we import. It would be great if you do that, but at least read the documentation. Next idea is cold storage. Is anybody familiar with cold storage, like the concept? Okay, a few. That's good. Actually, you will be, when I will introduce, you will be a bit angry because this is another storage. I just told you, please be very conscious about adding complexity, care about it, and I'm suggesting you to add another one. Okay, the thing is that I believe I have a good point here. Why adding another storage? Well, the thing is that at Zendesk we have a lot of data. As I was saying, 20 billion tickets, trillions of objects in one table only. This is obviously problematic. What if there was a way that those trillions of objects wouldn't exist in the table anymore? You can send them somewhere else. That's it. Well, it would be nice, no? Well, the idea is that you can. Nothing blocks you from doing this. Basic idea of cold storage is that there is some data. All data is not equal. Some data is just read a lot. It's hot data, let's call it. And some data is cold. It's just kept there for historical purposes. You don't really need it that much. So what we do at Zendesk is literally we send all data to somewhere else. Let me give you an example. This is like a mini Zendesk where a user has many tickets and tickets has events that are like an audit. And after some time, we literally mark that data as ready for being archived. Currently, the policy is that when a ticket is closed after a couple of months or 3 months, I don't remember exactly, we mark it as ready for archival, and we have a daily job that, well, processes it. Processing the archive data means removing it from relational database, but don't be scared, we just move it somewhere else. We have a specialized called ticket storage that is currently Dynamo. Before it was React. And we just send all data there. So tables stay small because we just have less data there. Of course, you may be thinking, well, this is very dangerous in multiple ways. One thing that we do to reduce the danger is that we create a different kind of ticket, called archive ticket, which is like a way, way thinner version of the original ticket. So we can keep, for example, associations there, or the most basic things like title. But still, most of the data is in the cold storage. This technique is super important at Zendesk, meaning that the vast majority of our data is in cold storage. We have around 9 times more data in the cold storage than in the hot storage, like the relational database. Of course, if you think about it, this has a lot of trade-offs. You are introducing multiple sources of data for what is basically the same data. I mean, if you think about it coldly, an old ticket and a new ticket should be the same. But at the same time, for architectural purposes, we decide that they are not the same anymore. You may even have to change access patterns. Because again, just imagine an API endpoint that gives you all the tickets. Suddenly, this endpoint needs to call 2 different storages. This may or may not make sense. For example, try to order 1 billion tickets that are in different storages. That's going to be hard because you're going to have to do it in memory, most probably. But now that we was talking about changing the product, changing the way that people access data, let's talk about one of the coolest parts, that is changing the product to make it scale. Because sometimes performance is not only, oh, I have this problem as an engineer, I need to solve it. It's also negotiating with the problem. Fortunately, there is something that is very, very simple to do, and it helps a lot. It's probably the technique that helps a lot the most to scale, is establishing product limits. First of all, one thing you need to understand is that when a platform gets to a certain size, you have absolutely no idea what's happening there. The other day, I was reading an article saying that majority of communication on the internet was in between bots, and I totally believe it. Moreover, you find customers that take your proposal, like for example, we're a customer support company, but they just decide to use to make a logging system for their own purposes of it. Because if you, for example, don't put a product limit in the amount of tickets, they can use it for storing whatever, if it could be Google Drive or something like this. Again, I understand that product limits are not sexy, but you are not understanding well the question. There are product limits here. In all your applications, there are product limits. Because applications run on the material world. The material world has limitations. So eventually, the product limit is the database meltdown. This happened. I think it happened to everyone. And of course, the question here left is, what is a good product limit? I will tell you. If you don't think, you have no clear idea, just imagine the biggest possible use for your application. You see, Cristian, nobody ever is going to have more than 100 users in one account. Fantastic. Product limit, 1,000. When someone tries to create 10,000, you'll be super happy you have that limit. And this happened to us again and again and again. The problem is that when a customer gets to a limit that is completely abnormal, you need to grandfather him to the future. Even if you set up the product limit later, you'll have customers working in ways that are very strange. Next issue with product design is what I call the incredibly enlarging payload. And I think that everybody that has been in a company for a while has seen this. The ideas are endpoints that return way too much data. Probably imagine you join a startup and you create this new endpoint and it's thin, it's nice, it's returning only 4 attributes per object, it goes really fast. But there is this thing called feature creep. You start adding features, features, features. That means attributes, attributes, attributes. And suddenly you have this monster is returning 40 attributes per object. And this means that it's slow. It's way too complex to understand what that endpoint is doing anymore. And just the payload is too heavy. You are just sending megabytes around the internet and you don't understand what's happening anymore. There are solutions for this. You should just define the core of the object, pass it, return it all the time, and then the rest are just options. You can use side loads, or one option that we like more and more is GraphQL. The final technique I wanted to comment on the product side is breaking down slow workflows. You can do this in both in the read and on the write. On the read, this may seem like a very, very stupid idea. you have this slow endpoint that returns a lot of data. Let's divide it into 3 new endpoints that return the same data as before. And this sounds stupid because you have to run exactly the same logic, so the computation time is the same, plus the network time, plus all the middleware. So the total is just significantly worse than before. Well, the reason why I recommend this is that you need some data fast, typically in a UI, so users can operate with it. You don't want your users to wait 5 seconds because you need to fetch some incredibly obscure data that they are not going to use. Dividing it like this improves the user experience. And in the end, for a vast majority of the products, user experience is king. Next, on the right, the idea is simple. Again, feature creep. You had this post endpoint that did something very simple, but now it's doing more and more things, changing more and more tables, different storages. It's crazy. The idea is going back to the simple part, keep the simple part synchronous, and the rest make it asynchronous. I think the REST community has embraced this a lot using Sidekick typically. At Zendesk we use Rescue, but well, the idea is kind of sound. You just keep the basic functionality synchronous, and then the rest to some queue that will be processed eventually. This actually goes naturally evolves into distributed systems. At Zendesk, we do a lot of event sourcing. We use Kafka. Every time that there is an update in our database, this typically generates multiple events that are processed or by our own monolith or by different microservices that do their own writes. Of course, one thing I wanted to comment is that eventual consistency can be painful. But ironically, the people having problems with eventual consistency are developers. Developers is a very different way to think about a system when you go asynchronous. Customers typically don't realize most of the times. A few months ago, we had this new feature that was going to make some part of the system asynchronous, and advocates were really worried, like saying, well, let's see what's going to happen. We'll get you feedback as soon as possible. We GA'd the feature, and after a month, advocates came back to us saying, hey, we are ready. When are you enabling it? Nobody realized. They had no feedback because all customers didn't notice the change at all. Okay, we're getting to the end, and I wanted to comment something that I believe is very important. Is what I believe is the right mindset for an engineer that works with performance and scalability problems. It's kind of simple. You just need to be like Alexander the Great. No, let me explain this. I don't know if you know the story of the Gordian knot. I will explain very briefly. Basically, it was the year 333 before Christ. And Alexander was in his wars against the Persians, I believe. He was crossing the city of Gordian. And there they had this legend. There was this crazy knot that was impossible to untie. And there was a legend that the man that would untie the Gordian knot would become king of all Asia. Of course, Alexander had like imperial ambitions. So he decided to give it a try. But it was impossible. He spent hours and hours and hours, and he just couldn't. Eventually, he took out his sword and cut the knot. Okay, I'm going to make a confession here. When I read this story first at 12, I think, I thought, so the point is that you can cheat? I mean, like, you are supposed to untie the knot. Why is this okay? But eventually, when I became an engineer, I understood. There is no requirement here of how to untie the knot. And I believe that we engineers do this a lot. Like, we get a problem and we put our assumptions of how the solution needs to be done. Why? This actually happens a lot when you talk with some other engineer about the same problem, that they take completely different assumptions about how the problem needs to be solved. This happens a lot with in conventional data solutions. Like, I believe because in computer science school, we get pushed a lot the idea of this immaculate relational normalized database that is perfect. But believe me, you don't need to be worried about duplicating data, caching. You need to be bold. It's about fixing the problems. Moreover, in the direction, you need to understand that engineering work, and particularly performance work, is about trade-offs. A lot of times, you're going to make a read way faster by making the write a little bit slower. And that's okay. Most of our applications are heavier on the read than on the write. So that would work. The other day, I was talking with an engineer, and he told me, hey, we found this way of making event consumption so much more reliable, but deploys move from 2 minutes to 10 minutes. And I was like, who gives a crap about a few minutes more on deploy when we deploy twice a week? It's going to be about trade-offs all the time. My final point is that there's no such a thing as a perfect system. Just a system that fits the best the current needs of the business. And finally, I wanted to say that in my experience, an excessive pursuit of perfection is counterproductive. The good news is that I think in the Ruby community, we are very well positioned about that. We are the only community that optimizes for developer happiness. We are the only community that understands that a happy developer becomes more productive and builds better systems. And finally, I wanted to leave you with a few words from Mats. I believe that the purpose of life is, at least in part, to be happy. Based on this belief, Ruby is designed to make programming not only easy, but also fun. Thanks.